Hello, my name is Lou Ferraro. I'm a security architect with AMD. And we're here to talk today about an update to the OpenPRoT project. We first announced OpenPRoT at the OCP EMEA Summit back in April. We had three main goals when we created this project. First of all, we want to create an OCP specification to define a platform root of trust stack. Secondly, we want to create an open source implementation of that specification. And finally, probably most importantly, we want to make sure that that firmware stack can run anywhere we need it to. So the intention is to be able to target both existing hardware root of trust as well as new upcoming implementations. So as we're going through architecting and building this stack, there are a number of pillars that we're trying to keep in mind to guide the architecture and the design work. First of all is implementation consistency. We think it's very important that we create a functioning reference stack that shows how to use OpenPRoT. We're starting out as using it for a platform root of trust, but we envision that it could potentially be used for other use cases, perhaps a rack manager, or even scaled down to client use cases. Transparency and openness. Obviously, we're here at OCP. We all understand the benefit of doing everything out in the open and collaborating with partners. Reusability. So along with that collaboration, we're working with both standards bodies, other root of trust projects, including Caliptra, to make sure that we're developing a reusable modular firmware. In particular, we're taking the SPDM and PLDM stacks that are being developed for Caliptra MCU, and we're building on those and also isolating those as independent standalone libraries so that we can share them between both projects. We're supplementing where we need to, and then eventually we will feed those back upstream so that both projects can benefit from this work. And then finally, interoperability. So by developing everything to open standards, whether that be the OCP standards, DMTF, or PCI SIG, we're making use of open standards, well-defined protocols to make sure that this implementation can be dropped in and easily integrated into any environment. So some project updates since we first announced this back in April, excuse me. We are now officially supported as a project under the CHIPS Alliance. In fact, that just happened last week that we were voted in by the CHIPS Alliance board with everything licensed under Apache 2.0. Our spec is in a 0.5 draft form at this point, available on GitHub. We do have some more work to do before the end of the year to get it fully to a 0.5 level. So we do welcome feedback and contributions at this point. We make sure it's as complete as it can be. Our reference stack the construction of our reference stack is underway. We're working right now with one of our IHV partners, ASpeed, to develop that stack on their AST 1060 PROT chip. And then moving forward from here, we're targeting to have a functional demo that we can show you along with a 0.9 rev of the spec by OCP EMEA next year. Now, when we first started this project, it was created by the 5 companies you see across the top row, the founding partners. But since then, we've had a number of other companies reach out to us that believe in the vision of what we're doing. So we have a growing ecosystem going at this point, with at least 6 more companies that have signed on to help us create the full stack. And there's more that we're in talks with that we think are going to be joining in the very near future. Hopefully all your companies will become part of that as well. And with that, I'm going to turn it over to Ravi from Rivos, one of our new partners, to talk about some use cases.
Thanks, Lou. So I work on security architecture at Rivos. So I wanted to just highlight some of the key building blocks that really show the value of a firmware, a standard ROT firmware layer like OpenPRoT. We've been going through this journey of taking some of these open, secure silicon IP blocks, and we were working with the OpenTitan project, which, as folks pointed out earlier, has actually built a lot of the IP building blocks that have been used by Caliptra as well. So we're really glad about that, and we're happy to contribute to OpenTitan. And we've added a bunch of things that we thought were missing in terms of this open security silicon. When you integrate such a root of trust engine into a larger SOC. Some example things are like, how do you consistently convey SOC debug policy, right, across the SOC, starting from the root of trust, which is your real control point, right? How do you enforce a register-wide access control policy, starting again from the root of trust, so that you can consistently say what IP can talk to another IP and so on. How do you enforce identities for keys through different life cycles as different entities are taking ownership of that part, starting from a silicon creator, going to a platform integrator, going to a platform owner, right? And all of these IPs are really exercised through the firmware stack, right? So that's really where the value gets unlocked, right? There's a lot, as Lou mentioned, there's a lot of value behind implementing standards at the interfaces level, whether it's IETF interfaces for attestation, or we heavily use DMTF interfaces like SPDM, and we'll dive a little bit deeper into that. But really, a lot of these differences across the security silicon can be abstracted and should be abstracted by the firmware layers, which is really where OpenPRoT plays an important part going forward. So looking at some of these use cases that security silicon like OpenTitan or Caliptra enable, that really bubble up to the top when you're looking at it from the firmware interfaces, is really all of the things that you use a platform root of trust or an integrated root of trust for, right? Whether it's secure manufacturing, like the provisioning provenance stuff that folks were talking about today morning. How do you interact with the device through manufacturing firmware? You're still running firmware at that early provisioning stages after the initial ROM boot stages. The entire SOC lifecycle, as the platform is changing its ownership, you're again running provisioning and bootstrapping firmware at different stages, sort of enforcing this security interlocks as the ownership is changing hands, right? For the overall platform TCB, whether you're doing secure boot or updates from these different roles, and as for other use cases, and I'll dive into that one a little bit more detail, because that's where like a lot of these interfaces that we exercise through SPDM come to light, like confidential computing, for example, where you need those interfaces to be able to validate the authenticity of the SOC, right? Validate that the right entity is putting the secure firmware on it, so that you can then ensure you're handing it off to the right next entity, or providing the right assertions which act as evidence when you're providing it to a relying party for use cases like confidential computing. So let's take that SPDM example, and I'm showing the stack on the right-hand side. As Lou mentioned, SPDM is agnostic to the underlying transport. It runs over MCTP, PLDM. We also heavily use it over PCIe, DOE mailbox interfaces, right? And these protocols that run on that secure session, and I'm showing you a couple of examples here. Things that are used right now are IDE key management, where you're sending up keys between like a root port and an accelerator endpoint, or TDISP, which is another protocol that's standardized for TEIO to enforce that when you're assigning accelerator interfaces to confidential VMs or confidential workloads, the confidential workload can actually verify that the endpoint that it's talking to is in the right state. And it might be the entire device, the entire accelerator, or it might be like a unit of the accelerator, like a virtual function, right? So exposing those interfaces through a standard interface like OpenPRoT is super critical, because you don't want everybody to struggle with different attestation formats. You want a standard interface so that you can talk to any accelerator and say, hey, what device am I talking to? What unit of the device am I interacting with? What state is in it right now? Does it have the updated firmware? Who's the vendor of this firmware, and so on. And this is just, again, an example slide which dives yet another level deeper into, if you look at confidential VM extension, and this is showing the example of the RISC-V standard that's work in progress in the RISC-V International organization called COVE, or Confidential VM. It follows the same paradigm that we see being used in the industry, where folks can run workloads in confidential VM instances, right? In this case, it's showing running it on RISC-V architecture, but we see similar design patterns, whether a confidential VM is running on a Intel TDX-like architecture, or an AMD ACV SNP-like architecture, or an ARM confidential compute architecture, right? So a lot of the workload approaches are sort of converging on that sort of a model. But what's really important is the underlying interfaces that are being used by these confidential VMs for attestation, for validating devices, things like that, really should also be based on common open interfaces, right? A lot of value for security comes from common open interfaces, whether it's the security silicon that's being used on the platform, whether it's the ISA that's being used on the platform, or it's the software and firmware interfaces being used on the platform, right? So with the blue arrows, I sort of wanted to just point out that no matter what layer of the stack you're interacting with security, it's all about your TCP, and it's really important to have open interfaces, which a design community can look at, a security community can look at, review, and provide feedback, and really harden over time, right? So we've kind of gone through that journey with OpenTitan, with Caliptra, and I think it's time to kind of look at the next layer of that interfaces, and OpenPRoT is a great start in that space to start standardizing some of the firmware interfaces. So with that, we'll go to the call to action and hand it over to Miguel from Google.
Yeah, so we just got the last slide. Is it okay now? Can you guys hear me? Yeah. Okay. Yeah, so this is our call to action. There are a few different ways to contribute to the project. You can join our mailing list. We're in the process of setting up a working group with a weekly or bi-weekly cadence. So we're hoping to see you there and participate as we discuss the specification details. We're aiming to have, as Lou said, the specification version 0.9 by end of Q1 next year. So it would be really great to see more faces there. The code is open source and publicly available now. We have an OpenPRoT organization managed by the Linux Foundation. So you can go there and start taking a look at the documentation and what we have work in progress. Yeah, so with this being said, I think we can take some questions now.
Hi, this is Quinn. I come from Alibaba. I'm the Alibaba Cloud BMC architecture. I have one question about the PRoT. So currently, any suggestion for the physically style, for example, the dedicated secure chip or integrated into the BMC chip for the firmware mastering, like BMC and BIOS.
So excuse me. So is your question about whether and where we see the OpenPRoT stack running? Is that what you're asking?
Yeah.
Yeah. So that really depends on the system builder and how you want to put your layout together. It's certainly we're looking at it initially with some of our partners as a standalone PRoT chip on the main board. There's no reason it couldn't be run inside the BMC if that makes sense for your design. We're really trying not to prescribe what the hardware is going to look like here. It's really up to the vendor and the customers to figure out what's the right layout for a given project. So we're doing that by making sure that we have a well-defined hardware abstraction layer. So as long as OpenPRoT has the interfaces it needs to talk to those hardware layers, we don't really care where we're running.
Okay, got you. So currently, whether there any reference design here to use different solutions, for example, the dedicated secure chip, and another is the integrated integration solutions. There is currently the reference design there.
Yes, so as Ravi was mentioning, they are looking into using the OpenPRoT stack in an integrated configuration. On our end, Lou, as he mentioned, we are also putting together a reference stack that runs on a discrete component. what we call the platform proof of trust. That's the A-Speed IST 1060. So we cover both. One thing that we'll be resolving over time is understanding what are the hardware requirements if you want to get OpenPRoT compliance, right? We'll have to define what additional requirements are needed on the hardware if you want to be compliant. Yeah.
Okay, thank you.
Hi, I noticed that the Caliptra subsystem uses a Talk OS and OpenPRoT uses a Hubris OS. Could you elaborate perhaps on why there are different choices made for operating system? Or is it just kind of each project did their own thing?
Yeah, no, we did take a good look at both of them as well as a couple of other options. The reason we decided to go with Hubris was really the fact that each task is completely isolated from each other. It's a microkernel model rather than a monolithic kernel. So we were looking at it as if you know, we want to make sure if one component goes down, it doesn't take down the entire system. That's the primary reason that we went with Hubris.
Yeah. So on our end, we're also interested in reducing code size and being able to work with a microkernel gives us the ability to focus on optimizing for code size as well. And also, in some cases, with respect to driver integration, it's a lot easier for us to move some of the drivers into user space.
Yeah.
And so it gives us a tighter control on the TCV. So when looking at things like FIPS certification, we could basically narrow down the boundary of the CMVP module. So that's also part of the reason.
Hi, thanks for the presentation. So in one of the slides, you mentioned that PROT could be used for CC use cases, confidential computing use cases. So in the CC case, mostly like it's the guest TVM, which is the tester, right? So how do you see that PROT would be used as a tester or it would be used for
the primary interface is like when the PROT is in this case like really running as on an integrated root of trust,
yeah.
acting as a SPDM responder, right?
Okay.
That's one of the key use cases. There are other scenarios where, so this is sort of assuming where your integrated root of trust is on an accelerator device, for example, right?
Okay.
What we are observing is, as somebody also mentioned, UCIe, right? Like most chiplets will be built with some sort of a root of trust, integrated root of trust, right? It might differ in profiles, right? But most entities are going to have to respond to some sort of authentication request from either another chiplet or from a BMC, etc., right? So, and the same thing holds true in the confidential computing case, right? When you have a accelerator function and you want to basically attach it or bind it to a CPU complex workload, right? Or another accelerator, for example, if you're doing peer-to-peer,
Yeah.
It basically serves as a SPDM responder primarily, right? In that case. Now you can do peer-to-peer, so you can mutually authenticate. SPDM allows for that as well,
Right.
right?
Right.
That was sort of the intent.
But usually the EROD, embedded rod in the device, is the SPDM responder, right? So is PROT assumed to be a embedded rod in the device, or is it going to be external and aggregating something from all the devices? Like, how do you see it?
I think those are different roles, right? Like what we were observing here is like the stack is usable, whether your ROT is an integrated ROT on a device or an accelerator or some processing element, or is in a manageability function like a BMC, acting
Okay.
like a PROT aggregating stuff, right?
Yeah.
In that case, you're also acting like an SPDM requester, right? Authenticating the different parts, right? But I mean that is sort of really up to like your system architecture, right?
Okay. Yeah, but Caliptra is already in that space, right? Where you have it can be used as an embedded rod. It also has this SPDM stack inbuilt. So I was thinking this is more like a standalone usage where you have something like this on the platform or integrated as part of the BMC. Is that right?
I think it works. Like we're sort of agnostic to that. Is kind of
Okay.
what we're observing.
All right. Thank you.
All right, no other questions? Okay, thank you.